In this video, we're going to introduce an important group called the symmetric group on a set A. Okay, so let A be a set, and for example, A could be the set of integers 1, 2, 3, and 4. Then the first thing we need to define is a permutation of the set A, and that's simply a bijective function f, for example, from A to A. So here's an example. So let's take A to be the set consisting of just these numbers 1, 2, 3, 4. And here on the left, I've given an example of a bijective function. So remember, a function is something that has an input side and an output side. And in this case, the input and output are both the set A. And according to this illustration, f of 1 equals 3, f of 2 equals 1, f of 3 equals 2, and f of 4 equals 4. So I've just defined a particular function, one of many, that has A as the input and A also as the output. And this is bijective. And what that means is that everything on the output side is part of the image. In other words, has an arrow pointing to it. And then also two different elements on the input side map to different elements under f. So this is an example of a bijective function, and so therefore this function f here, defined by this picture, is a permutation of this set A. By contrast, on the picture on the right of a function is not bijective, and the reason is a couple of reasons. First, this element 1 has nothing pointing to it, and so this function is not surjective, it's not onto. Another reason that this function is not bijective is we have two different elements on the input side that map to the same element on the output side. And so this function is also not injective. And so therefore is not a permutation. So we're going to be interested in the permutations, and the reason is they form a group. Okay, so let S sub A be the set of permutations of A. In other words, functions from A to A such that f is bijective. So the picture on the above left is one element of this set. This is going to be a fairly large set depending on how big A is. But okay, and so this is going to be the set of permutations. The elements are functions, they're not numbers. But okay, so it might be a little bit harder to think about what this set is. It's going to be a group, so we need a binary operation. And what's the binary operation? Well, it's function composition, or composition of functions. So this binary operation requires me to give me two functions, and I have to give you somehow a third function. And that's what you can sometimes do in pre-calculus, for example. Suppose the two functions are f and g, and then we define g asterisk or star f as a function from A to A that first does or applies f and then applies g. So there's several ways to write it. Here's the schematic picture. Here's another way to write this as g star f. If you give me an element in lowercase a in capital A as input, then the output is g applied to f of A. So start with A as the input, then first apply f, and then apply g. So even though we write f second and g first, we apply f first and then g. So this is what I mean when I'll say that I work from the right, because that's how function composition can be done. Okay, so then it turns out that g asterisk f is a bijective function, and hence it's an element of S sub A, the collection of all bijective functions from A to A. So we have a binary operation. You give me two elements in S sub A, I do this function composition business, and I give you a third element. Okay, so then the simple but important fact is that the set S sub A, again, just the bijective functions from A to A, or the permutations is another term for a bijective function, it forms a group under this binary operation of function composition, and that group is called either the permutation group of A or more commonly, the symmetric group on A. And again, the elements of S of A are functions, or maps is sometimes what I'll call them, not numbers. The identity element, every group has to have an identity element. So what's the identity element in here? Well, it's the identity function, the function that if you give A as input, it gives that same number A as output. It's a simple fact that if A has 3 or more elements, this group S of A will be non-abelian, in other words, non-commutative. And especially as A gets large, it's a very complicated group. And historically, S of A were the first groups that were studied, particularly when A was the roots of polynomials. So these groups arose before the term group even came into existence. Now, if we have two sets A and B, and they have the same size. For example, if A was 1, 2, 3, 4, and B was like 3, 4, 5, 6, so they both had 4 elements, then it's a simple fact that the symmetric group on A is isomorphic to the symmetric group on B. You just use this isomorphism of sets. And so it's really only the size of A that matters. The cardinality is a fancy way of saying size. Okay, so typically we just take A to be the finite set. Well, when A is a finite set, we take A to be the set 1, 2, 3, 4, all the way up to n, and call S of A the symmetric group on n letters. Now we typically say letters even though these are actually numbers. And then instead of writing S of A, we'll write S of n for whatever the number n is. Like n could be 4, and then we'll write S of 4. And it's a fact that the size of S of n is n factorial, where n factorial means you multiply all the numbers starting at 1, 2, 3, all the way up to n, or start with n and decrease by 1 down to 1. So S of 3 is a group with 3 factorial, in other words, 3 times 2 times 1, which is 6 elements. S of 5 has 4 factorial, 24 elements. Sorry, S of 4 has 24 elements. S of 5 has 120 elements. And the structure of this group, S of 5, contains the secret for why there's no quintic formula, a formula analogous to the quadratic formula, but instead of ax squared, it would begin or apply to polynomials ax to the 5th. There's no general formula, and the structure of this group reveals the secret for why there's no such general formula, and was the inspiration for why the study of groups arose and abstract algebra in general. Let's do a concrete example. So let A be the set 1, 2, 3, 4, all the way up to 6, and so we write S of 6 instead of S of A. And then let's pick 2 elements in this set S of 6. Let's call them mu and sigma, and they're given by this notation, which I have to explain. So mu is equal to this thing here, whatever this is, and sigma is equal to this thing. Well, mu and sigma are in S6, so they have to be functions. And this notation is shorthand for the function that sends 1 to 5, 2 to 2, and each number to the number below it. So, in other words, mu of 1 is 5, mu of 2 is 2, mu of 3 is 4. In terms of a picture, here's 1, 2, 3, 4, 5, 6, and then instead of labeling here 1, 2, 3, 4, 5, 6, I've jumbled up the order. But mu sends 1 to 5, 2 to 2, 3 to 4. Now my picture, 3 to 4, and 4 to 3, and so on. And then sigma is similar. I didn't draw the picture for sigma, but sigma sends 1 to 3, 2 to 1, and so on. Every number gets sent to the number below it. Okay, and so the question, this is taken from Frale, page 83, number 3, says compute mu sigma squared. So this is the group operation, is implicit in here. I left out the stars as usual. So this is mu times sigma, and the times again is function composition. In other words, we have to fill in the second row of this matrix here. this here is a function, and in other words, you give these numbers 1, 2, 3, 4, 5, 6 as input, and this question is asking, what does this function do when you give these numbers as input? Okay, so we have to start with 1, and we have to figure out what number goes here below it by asking, what does this function do to the number 1? And so we plug in 1 into our function mu sigma squared, and mu sigma squared is mu composed with sigma, mu sigma sigma, and then applied to 1. Now sigma of 1, if you look at what that was, sigma of 1 was 3. That's, we'll go up here, sigma of 1 is 3. And in a moment, we're going to need sigma of 3, so let's remember that's 4. Okay, so sigma of 1 became 3. And then we have to compute mu sigma of 3. Well, we just saw also that sigma of 3 is 4. And then we have to figure out what mu of 4 is. Well, mu of 4 from this picture up here, we can see that mu of 4 is equal to 3. And so the conclusion is that mu sigma squared of 1 is equal to 3. And so 3 is the number that goes down here. Likewise, we've got to fill in the rest of this. It's a little bit tedious, and we're going to find an easier way to do it. But on the next slide, I do a little bit more of the details. Okay, so once again, here are mu and sigma. I've just copied them over, and we have to continue filling in this second row. So the next we go to 2. What does this function mu sigma squared do to 2? Well, it sends, well, first of all, we have to figure out what sigma does to 2. Here's what sigma does to everything. So sigma of 2 is 1. So this sigma of 2 got replaced with 1. Again, we work from the right to left when working with functions. Okay, so then we have to figure out what sigma of 1 is. Sigma of 1 is 3. So mu of 3 is 4. And so that's what goes down here. Anyway, I've done all the rest of the computation. Here's the details, but I won't go through them. That's kind of boring. And again, we'll find a little bit of an easier way to do this. So finally, here's the final answer. And we'll again find a more compact notation called cycle notation that will speed up in figuring this question out. And then one thing I want to emphasize though is that even though there's lots of numbers floating around all over the place, the elements of the symmetric group, like S6, the symmetric group on 6 letters, if you will, are bijective functions. They're functions and not numbers. And then also remember that the group operation is composition of functions.